basically, a lot of different structures in space have magnetic fields. So planets, our Earth has a magnetic field, for example. Stars, including our sun, also have magnetic fields. So magnetic fields are basically everywhere. And it turns out that our galaxy itself that we live in is essentially a giant space magnet.
Welcome to the PAM Talks. Each episode, we interview a new physics and astronomy mentor, exploring the universe through the lens of diversity. I'm Pooja Woosaree, your host for this episode. I'm a PhD candidate in atomic and nuclear physics at the University of Calgary, working with the Alpha Collaboration in antimatter research. Get ready for a discussion on the galactic scale, because today I am interviewing Dr. Anna Ordog, a postdoctoral researcher in astrophysics from the University of British Columbia, Okanagan, and the Dominion Radio Astrophysical Observatory. We call these UBCO and the DRAO for short. Dr. Ordog has been studying the skies above us, far, far above us. She's here today to tell us how magnetic fields shape our galaxy and the equipment necessary to image the Milky Way. This is the PAM Talks, where the universe is as diverse as the minds unraveling its mysteries. Coming up next, my interview with Dr. Ordog. Well, hello, Anna. Welcome to our PAM Talks podcast. Would you like to take a moment to introduce yourself?
Sure. Thank you so much for having me on the podcast. So my name is Anna. I'm a postdoctoral researcher and an observational radio astronomer studying the magnetic field of the Milky Way Galaxy, and I'm currently working at the Dominion Radio Astrophysical Observatory.
So I was wondering if you could start with, what is radio astronomy?
Sure. So radio astronomy is a branch of astronomy that's complementary to optical astronomy. Basically just observing at a different range of wavelengths. So a much longer wavelengths typically than you have with optical. And this is looking at electromagnetic radiation from space that is not visible to the human eye.
Okay, very cool. If it's not visible to the human eye, then how are we actually able to see it?
So we have these instruments called radio telescopes, and they are essentially antennas that convert electromagnetic signals into electrical currents in a wire, and then those electrical currents can be interpreted as the signals that are coming from space. So the kind of funny thing is that radio astronomy was discovered by accident, and it's a field of astronomy that's only been around for less than 100 years now. The way it happened was Carl Jansky, who was working on transatlantic communications, accidentally discovered a signal in his data that he had some antenna that was picking up signals, and the signal appeared to have a periodic nature. So it would come up every not quite 24 hours. And it turned out that what he was actually seeing was emission from the galaxy as it rotated with the sky on a daily basis. So it was discovered in this way, kind of by accident. And then others built upon this once they realized that it's actually possible to detect these signals from outer space using antennas. And so nowadays, radio telescopes look very different from how they did in the early days when they were just these very, very simple antennas. But that's basically what they are. They're just antennas that convert electromagnetic signals into electric currents in a wire that can then be written down as just numbers as they were in the early days, or nowadays they're processed by computers and turned into images. A modern radio telescope consists of a reflector that just looks like a big satellite dish, basically, and then a receiver that's mounted at the focus point. So the radio signals bounce off of that dish and they're collected at the focus. And then, like I said, they're converted into an electric signal that can then be interpreted by a computer. So they operate very differently from an optical telescope.
Oh, yes, very different, because when I imagine you saying, you're looking at where the source of origin is for a lot of these signals, I'm imagining an ordinary telescope that we normally see. So this is very interesting. So it's essentially just a satellite dish, you're saying?
Yeah, it basically is. And in contrast to when you look through an optical telescope where, you look through it and you can actually see a patch of the sky. You can see maybe a cluster of stars or the moon or whatever you're looking at. You see an actual image of it right away. With a radio telescope, it doesn't work that way. Instead, what you have to do is point your telescope in a particular direction. All you get out of that is the signal that's coming from that exact direction. In order to make an image or a map of a region of the sky, what you have to do is scan with your telescope in like a very sort of densely spaced pattern to collect the data points as you go along the image and then produce the two-dimensional picture out of it.
Wow, that's incredible. You mentioned working at the DRAO, and I was curious, where is it and what does it look like?
Okay, so the Dominion Radio Astrophysical Observatory is located about 25 kilometers south of the town of Penticton in British Columbia. And it's actually located on the traditional lands of the Syilx Okanagan people. And we're very fortunate to be able to have this really, truly beautiful site on which the observatory is located. So it's sort of in a valley up in the hills south of Penticton, surrounded by mountains. And those mountains offer protection from radio interference signals that can interfere with our measurements. And so it's truly an amazing place to see. I highly recommend going there on a tour. We're open in the summers and on weekends. You can just drop in and take a look around site.
Very cool. All right, Anna, can you tell us a bit more about your research specifically at the DRAO?
Sure. So I am studying the magnetic field of the Milky Way Galaxy, in particular, trying to map out in 3 dimensions, ideally, what the structure of that looks like. So basically, a lot of different structures in space have magnetic fields. So planets, our Earth has a magnetic field, for example. Stars, including our sun, also have magnetic fields. So magnetic fields are basically everywhere. And it turns out that our galaxy itself that we live in is essentially a giant space magnet. So we are basically trying to map out what the magnetic field lines covering the region of the entire galaxy look like. And when I say magnetic field lines, what I mean is representation of the direction that a compass would point if you were able to go out and walk around in the Milky Way Galaxy and figure out at every point in space which way your compass would point.
And I think the way we normally understand, walking out with a magnet is that we say, okay, the magnet's going to point north. And I think that's simply because we assume our planet is like a dipole magnet. Can you say the same about our Milky Way?
Yeah, so basically, can we say that the galaxy has a North Pole and a South Pole, and it's sort of a nice dipolar structure like the Earth? Less so than the Earth. I think the structure is more complicated in a lot of ways. There is some evidence to suggest that there is a dipole-like structure that sort of emanates out vertically from the center of the galaxy, with the field lines going initially perpendicular to the disk of the galaxy, which is the flat circular part, and then kind of raining down and closing back in on themselves in this sort of dipole structure. The Milky Way has this disk component as well, which has the material spiral arms in it, where you have higher concentrations of gas and stars. And there are magnetic field lines that also sort of follow along those spiral structures as well.
So I guess we're all curious. The magnetic field, what does it do?
Magnetic fields, magnetic forces, are one of the many forces that contribute to how the matter in galaxies produces various structures, how galaxies themselves form and evolve. And so it turns out that magnetic fields, understanding them, are a really important part of that puzzle of learning how galaxies actually came to have the structure that they have and how they evolve.
Okay, so you're saying the magnetic field of the Milky Way is something we should be very interested in. And I'm just wondering, why? Is there no data on the magnetic field of the Milky Way?
There's a bit of a problem of not seeing the forest for the trees because we're embedded within the Milky Way and we're trying to see through it and see all of the structure. But some of the difficulties are that, well, first of all, magnetic fields themselves don't radiate. They don't produce any emission. We can't just see them. And so we have this indirect way of observing them. We do this by looking at polarized radio observations. So we have polarized emission that comes through the galaxy. And it's a very good probe of the magnetic field because there's a phenomenon known as Faraday rotation. And what happens with this is that if you have linearly polarized electromagnetic radiation that propagates through a region that has charged particles, so electrons floating around, and a magnetic field, the polarization angle actually undergoes a rotation as the wave propagates through. And so by studying that polarization angle with radio telescopes, we're able to calculate some information about the magnetic field along the sight lines that we're looking at.
Okay. Now, I'm a very visual person. I'm also an experimentalist, but more so in particle physics. I guess in a way, we have more direct data. Could you tell me what it means to observe a rotation? This for me in my head is not something I can visualize.
Yeah, so actually observing the rotation is hard, and we can't do that directly. We can't actually say, oh, we're going to look at where the emission started and where it ended and compare the rotation from start to end. That we can't do. All we can do is measure the polarization angle of the emission that arrives at our telescope. So for this, we can build our instruments in a way to have probes that are sensitive to the vertical component of polarization, the horizontal component of polarization, and then you combine those with some trigonometry magic, and you get a polarization angle. And so all you know is that angle that arrives there at the telescope. And the key thing that's very convenient about Faraday rotation is that it's a wavelength dependent effect. So you have more rotation for longer wavelengths of electromagnetic radiation and less rotation for shorter wavelengths. And so with your radio telescopes, if you observe over a really broad range of frequencies or wavelengths, and you compare what happens to the polarization angle at those different wavelengths, you can then infer something about the magnetic field structure. The other key component is that this rotation is also proportional to the magnetic field strength. So the more rotation you're seeing, that's indication of a possibly stronger magnetic field along the line of sight that you're probing. So that's how you kind of connect the observations and what we're ultimately trying to map.
Okay. This is a lot of measurement to happen over the course of, I suppose, making this map that you're trying to visualize of the entire galaxy. A tremendous amount of work must go into this. So surely you're not the only one working on this?
Absolutely not. This is a global effort spread among a number of different projects, actually. So one aspect of this is that we can only observe about 2/3 of the whole sky from the northern hemisphere. The other 1/3 is invisible to us because the Earth is always in the way. And so one thing that we definitely need to do is collaborate with astronomers in the southern hemisphere. There's a big radio astronomy community in Australia, so we collaborate with them in the sense that they're producing maps of the portion of the sky visible from the south, and we produce the ones visible from the north, and then you combine those. And so this leads to these large global collaborations. But even within those groups, there's an immense amount of work being done in very different areas. So there are the scientists like myself who, for the most part, we analyze the data and interpret the data. But then, of course, there are people who work on the data processing itself. So it's not images directly that you get off of these telescopes. It's just a whole pile of data files with numbers in them. And so people need to work on processing those. And then if you take it even a step further back, there are the people who build the instruments themselves. So the engineers, technologists who build the telescopes in consultation with the scientists and, build the control systems for them, write the software that collects the data, figure out ways to store ridiculous amounts of data because, the astronomers always want better resolution and better time sampling, but that leads to sometimes truly ridiculous amounts of data that need to be stored. So yeah, many, many people involved across a really wide range of disciplines.
There's no shortage of roles in radio astronomy. Okay. This sounds like a really difficult task because one, you can't see the magnetic field, as you say, and you can't make direct observations. You're taking weeks to years to even produce an image. What are some of the other big challenges you come across in your research?
So one of the big challenges with radio astronomy is human-made signals that interfere with the signals that we're actually trying to look at. So much in the same way that if you have bright lights around an optical telescope or an optical observatory, it's going to be really hard to be able to see faint stars in the sky, or maybe any stars. You know, you go to the Rothney Observatory near Calgary, and these days you can very much see the glow of the city, and it sort of prevents you from being able to see very faint things on the sky. So the equivalent of that in radio astronomy is basically cell phones and television stations. So these produce radio waves as well. They're all around us. And there's sort of an irony in this, because the same kind of technology that allows us to have cell phones that are as powerful and versatile as they are, this is the same kind of technology that we can actually use to make better radio telescopes. And so it's kind of a race between technologies, but that is one of the biggest challenges.
Wait, so you're saying you can show up to work and not have your cell phone on you, but
yes,
be able to use the same technology to make observations?
Absolutely. So when we go to work at the observatory, first thing before we even get to site, shut off our cell phones, and you can see them in the data. So there are times that we have visitors on site or contractors doing various work who may have missed the memo about needing to turn off their cell phones. And there have been instances when, you know, we're observing and we collect data and we see, oh my gosh, there's a mess in this hour of data. What was going on there? And it turns out someone was walking around with a cell phone. So it shows up in the data, it contaminates the data, and there's really no recovering the sky signal from a portion of the data that's contaminated by that. But there is this sort of separation where, you know, if I'm sitting at my computer doing work, I don't have my cell phone beside me. So it's kind of nice, actually, a way to focus.
So to end things off, what is the future of your research and for radio astronomy?
So there are some really exciting times coming up, I think, for radio astronomy. One of the biggest projects that is currently underway in radio is called the Square Kilometer Array. So this is an international project that the goal of which is to build an array of radio antennas that work together to produce images of the sky in a process called interferometry. And the intention is that they will cover an entire square kilometer of collecting area. And so that's to achieve the kind of sensitivity that a lot of projects require. This array of telescopes is going to be located in Australia and South Africa. And it's been in the works for a few decades now, actually. But there have been some Pathfinder or prototype versions of the telescope that are already currently producing data. And Canada has been involved in a lot of the technology development for this already. And now the National Research Council of Canada has committed to becoming a full member of the SK Observatory. And so I think this is going to mean a lot of great opportunities for future generations of young radio astronomers. So I think it's really a good time to get into this field of research. I think we're in for a really exciting time because of projects like this coming up.
Yes, absolutely. And I have to say, it seems like to take any of the next steps in science, collaboration is key, like these getting together and sharing knowledge.
Yes, absolutely. Science is very much a team sport. So in my experience in this postdoc so far as well, I've been involved in two large collaborations. One is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. So this is a primarily cosmology project, but it's branched out into a bunch of other areas as well. And then another collaboration called the Global Magnetoionic Medium Survey. So this is a bunch of people from around the world who are all really keen to understand galactic magnetism. And so, yeah, with these groups too, I've met so many amazing people that I've gotten to work with and have learned a bunch. It's not, science is not sitting alone in a room and coming up with the next big discovery. The big discoveries are really coming from these large collaborative types of approaches.
Thank you, Anna. And thank you for joining us today on our PAM Talks podcast.
Thank you so much for having me. This has been a blast.
Well, that's the end of this episode of the PAM Talks. Thanks so much to Dr. Anna Ordog for joining us. In this episode, we discuss galactic size structures. But next time, we're shrinking down to the tiniest scale in an exploration of quantum computing. Join us as undergraduate student Amina Hafaz interviews Pragati Gupta, a PhD candidate in quantum science. Get ready to explore the universe through the lens of diversity and join us in celebrating the brilliant minds breaking barriers in physics and astronomy. The PAM Talks gratefully acknowledges support from the University of Calgary Graduate Student Association Quality Money Grant.